Okay, I think we'll get started. So today we're going to talk about the derivative of the Blaschke product, the logarithmic derivative, and then the critical points. Critical points are where the derivative is equal to 0. All right, so we've learned now that we can talk about the normalized Blaschke product, and the things we do with that we know are related to all Blaschke products because of this ability to compose Mobius transformation before and after the application of the Blaschke product. So we're going to work now with the normalized Blaschke product, and we'll just use this lambda. We won't need it here. This is just the phase that comes in. So here is the functional dependence on z, and then we have one of the zeros set equal to 0. That just comes out as a z, and then this phase is such that if we plug in a z equals 1, then the Blaschke function is equal to 1. Okay, so a very common derivative, or a very common function that we generally make from analytic functions is this function here, which is the ratio of the derivative over the function itself. So we know this will have poles at where the b is 0, although there is some complications when we have double zeros, because then the derivative itself is 0 there as well. But by the chain rule, this is the same as the derivative of the log, so this is referred to as the logarithmic derivative of this analytic function. Okay, well, let's do the log first. And so the nice thing about the log is it will turn this product into a sum just by properties of logs. And so we'll get log of z, then we'll get log of each one of these up to n minus 1, these phase terms, which has no z dependence, so that's going to just go to 0 when we take the derivative. And then we have logs all of terms of this type, so they're going to have the same derivative when it all is said and done. Okay, so let's take the derivative. So we take the derivative of log z, and we get 1 over z. These go to 0, and then these, you have to kind of work it out, but you take the log of, or the derivative of this, and we get 1 minus the 0 mod square, and then z minus the 0, so that's this numerator term, and then times the denominator term. So this is how the derivative works out. Now we can write this succinctly as then a summation. So we have 1 over z that we pull up front, and then we have the sum from, again, k from 1 to n minus 1, collecting all these terms here, and then just replacing the zeros with the k 0. Okay, so that's our logarithmic derivative. So if we want to find the zeros of the derivative, then we can just we could set this over a common denominator and solve the numerator equals to 0. And sometimes that's easier than just doing the derivative itself. Kind of depends, but often it's easier, with the caveat that we have to be a bit careful when we have 0 of degree more than 1. And we'll talk about that via an example here. So we'll just go through some examples and see how things work. So let's take the simplest Blaschke product that isn't just a Mobius transform itself, and that would be a second degree Blaschke product. So by our formula here, we have 1 over z, and then we will just have one term in the sum, because we're summing from 1 to n minus 1, n is 2, so 1 to 1. Now, we put this over a common denominator, so we'll multiply this up, multiply this over, and we get this. Now, when this is 0, the derivative is 0, and when the derivative is 0, the values of z that make the derivative of the Blaschke product go to 0 are called the critical values, or critical points of the Blaschke product. So we're going to be looking for the critical points. All right, so we'll just set this equal to 0, and we get the single critical point here. And this is illustrative of the the theorem that we talked about when we were just listing theorems, and that is there's always n minus 1 critical values. So we expect 1 critical value. Now, this will come out, this is going to be a second degree polynomial up here, because we can see this z here and this z here. So this is really a plus or minus, but the plus version of this will take us outside of the unit circle, so, or of the disk. And we know we're limiting our space to just the closed disk. Okay, so this is just in general. Let's look at some examples, and we're going to use this example or examples built on this throughout the course here. Simple as we can kind of choose our 0 to be 0 and then some real value, and we'll just take this to be 1/2. And so this will be kind of a test function for us in several cases. So let's just use this formula in this case, and we end up getting this. We can simplify this. So this is plugging in 1/2 here. It's getting squared, so it's 1/4, and then complex conjugate of 1/2 is just 1/2. So that's where that is. When you work this out, we get 2 minus square root of 3, and that evaluates to about 0.26. I didn't quite draw that to scale here, but here is our zero. Here are our zeros, and then this is our critical point. And this is getting a little bit ahead, but we'll soon know we should expect the critical point in this particular case to sit between these two, and indeed it does. But we don't know that yet, so let's just make that observation. We observe that happens. Okay, well, let's step it up a notch, and we'll go to n equals 3. Now, even at n equals 3, it becomes a bit more difficult and a little bit too messy to really track through. You can do it with Mathematica, and I do that often, or just numerically, which I will do a lot, and we'll see that a little bit as well. But let's take a simple example here that we can actually work out with pencil and paper here pretty quickly in just a small amount of space. So this will also illustrate when we have a 0 of order 2 here in this case. So we're going to put this order 2 0 on the 0, and then take the z to the other 0 to be 1/2. Now we will come back and flip-flop that, but we know we could make that change anyway, so we really wouldn't need to do this because those two can be related through a Mobius transformation, and oftentimes we think of these Blaschke products sort of modulo a Mobius transformation. Even though they will give different values, they're related through the fact that they're just differ via a Mobius transformation. Okay, so here's our zeros, and we have a double 0 at 0, as I'm saying. Now, let's do the logarithmic derivative, and let's do the derivative. See what happens. So the nice thing about the logarithmic derivative is that the numerator here ends up to be a second order polynomial, and we would have expected third order. Now we might say, well, okay, maybe it is supposed to be second order, and both the critical points are going to be inside the disk. Well, you're always going to have one outside the disk, so that would leave us with just one critical point. And when we work this out, when we solve this numerator equal to 0, we do indeed get that one critical point. Now, it turns out that if we would have worked out just the derivative of d, we would have got a third order polynomial, but it would have factored into this times z, and so our other critical point is going to be z equals 0. Now, we should have anticipated that to begin with, because this is a second order 0. That means the derivative is going to be 0 as well. If it's a first order 0, then the derivative will not be 0 at the 0. But if it's higher than first order, then the derivative will be. And so we're always going to pick that up. And so the logarithmic derivative, often, if we have multiple, if we have at least one point with a degree 2 or higher, then the logarithmic derivative will often kind of simplify things and reduce us in power. And then we just bring back whatever is our multiple 0. All right, well, let's just compare that to this. And I said these are related through a Mobius transformation, but let's just do it directly. So if we would work through this, and we won't necessarily do that, but if you were to do this, and that might be a good exercise for you, see if you can recover this, see if I made a mistake there, or if you indeed get that. So instead now, we will take the logarithmic derivative of this, and we would get this point. And now we know that the double 0 is at 1/2, and so we have another critical point sitting here at 1/2. All right, so the zeros, the critical points, and the relationships in the disk between the zeros and the critical points lead to some really beautiful geometric emergence that comes out of this, which will be coming up later in this mini course. So important for you to get a good handle on taking the derivatives. Now, when things get higher than n equals 2 or these simple n equals 3, then it gets difficult to do it by hand. But you could set it up numerically, and we'll definitely do that. And just look at some of the results and explore the positioning of these critical values. All right, so I encourage you to maybe try a few others, see if you can, if you have access to, say, Mathematica, although that's a paid program, but Python, for example, if you could numerically calculate some of these with Python, or use SymPy and see if you can algebraically do it. I don't use that. I usually use Mathematica for the symbolic calculations. All right, so see you next lecture.